Okay, hopefully this is going to be a somewhat quick one, but also a very, very important one. We're learning about Newton's second law today, which is F equals ma. That means that force equals to the mass times by the acceleration. When you go on to mechanics in the second year, you'll see something for friction, which also uses an F, which is something I hate about the mechanics course. But you just need to know in this case, right now you don't know about finding friction, so it's not going to confuse you, but just so you know it, this F in the F equals ma is for force. Friction, some people might put Fr to try and distinguish between these two. So if we think about this formula, it seems very, very simple. And we'd like to think it was simple. If it's a law of motion, we want something that's intuitive, that you can just look at and think, yeah, that makes sense. So it feels right, doesn't it? If we double the force, we double the rate at which it accelerates. If I push something twice as fast, then it is going to accelerate twice as fast. And that's what this formula would do. If I double this, then and the mass stays the same, well, then the acceleration must double as well. And similarly, if we have an object with twice the mass, so if this m doubles, well, we would require twice the force to make it accelerate at the same rate. You'll surely know if you have something really heavy. Oh, Sheffield Wednesday just conceded. I'm watching that at the same time. Oh, it's offside. Brilliant. My apologies. If you've tried to push something heavy, you need more force to get it going at the same acceleration. So let's have a look at using it in these examples here. So it's really important to draw a diagram in this case, because when we get to more complex questions later in the chapter, a diagram is going to be the most important thing about it for you to get your head around what's really happening. So we've got a car of 200 kilograms. That's the mass. So if they give you something in kilograms, etc., that is a mass. So I'm going to draw my car, 2,000 kilograms. It's got a driving force. Well, I'm going to state that anything I'm drawing going this way is going to be a positive force. So it's got a driving force of 800 newtons. And it's got forces of 200 newtons resisting its motion. Determine its acceleration. Well, we could also label on its weight and the reaction force. But actually in this case, it's not going up or down, so that's not important to our diagram. It's just the left and right forces because we are moving along a road. So when I talk about the force, that is actually the resultant force. So if we're having 800 newtons pushing us to the right and 200 newtons resisting that motion, well, the resultant force of that is going to be 800 subtract 200. You need to see which direction are we moving, and you need to do the direction we're moving, subtract the direction that's resisting. And then the mass is 2,000. And then A is our acceleration. We don't have that yet. So we've got 600 equals to 2000A. We just need to divide by 2000 at this stage to find out what my acceleration is. So my acceleration in this case is 0.3 meters per second to the minus 2. So nothing too crazy there, it's just learning a new formula and getting used to using the values to find this. In the second example, well, a child has a mass of 50 kilograms. What is the gravitational force acting on the child, i.e. its weight? So I mentioned last lesson that the weight changes depending on our gravitational pull. So if you go to the moon, your weight will be significantly less than your weight on the Earth because there's less gravity there. But your mass stays the same. So this is a mass. And to get our weight, we need to do our mass and we need to times that by gravity. So that's going to be 50 times g. I can also do 50 times 9.8, because in maths we represent gravity as 9.8. So I would say that 490 newtons is your weight, because it's a force, your weight. So we measure that in newtons. Okay, and then this final one, well, the falling sheet of a mass 70 kilograms experiences air resistance of 300 newtons. Determine the sheep's acceleration as it plummets towards the ground. Bit of a gruesome picture to imagine, but if we draw our sheep, that's got a weight of 70 kilograms. Your diagrams don't need to be artistic, just draw a circle or a box for your objects. And if you have more than one, maybe put an arrow and say that's my sheep, that's my something else. It's got a resistant force of 300. Well, if it's falling downwards, my resistant force is going to be going up. And what's pulling it down is not 70, it's weight. So 70 times by gravity. So you can write that as 70g. Or if you're wanting to write it as a number, you could write 686. But I would always, in your diagram, label it up as g. So again, we're trying to find the acceleration. We're going to be using F equals to ma. Well, the direction we're moving is downwards. So to find its resultant force, we do the direction we're moving, subtract the resistance. So 70g subtract 300 equals to the mass, which is 70, times by the acceleration, which we are just going to call a because we don't know it yet. So this side is 386. So when we divide by 70, we get that the acceleration is 5.5, etc. 5.514, but because I've used gravity in this, I need to round to two significant figures, so I would actually call that 5.5, not 5.514, etc. And then let's have a look at an example of combining this with SUVAT, so how these questions get a little bit harder. How they get harder past this is we get introduced into different situations. We'll see that later on in the chapter. But mixing this in with SUVAT is also how they make it more realistic, and obviously makes it a little bit harder as well. So first I need to find the acceleration of the body. So how do we know to use this instead of SUVAT for this first part? Well, if we were given initial speeds and all of that stuff, we could, and times, we could use SUVAT, but as you read this question, you can see that we don't have really any information for SUVAT. But we have been given mass and forces, so therefore I can be using F equals to ma. So let's get a diagram drawn on this right hand side of what's happening. A body of mass 5 kilograms is being pulled along a rough horizontal table. So what I've labelled on there while I was talking was its weight and then the reaction force. It's being pulled along of magnitude 20 newtons, and its frictional force is 4 newtons. So that is my diagram. And we're going this way. I'm accelerating in that direction. So to use F equals ma to find the acceleration, I would do 20 subtract 4 as my resultant force, equals to the mass times acceleration. So then 16 divided by 5. The acceleration is 3.2. Okay, then in the next part, we've said the distance travelled by the body, we want to find, the distance travelled by the body in the first 4 seconds. So because they've started to introduce time, and if they could also introduce initial or final velocities, that's what's pushing me towards thinking, well, that's not included in my F equals ma formula, that's included in SUVAT. So I'm thinking, well, I can use Suvat now. So let me get my Suvat written down. We're wanting to find the distance travelled in the first 4 seconds. We know the acceleration is 3.2. Well, we need one more thing in here, given that the body initially is at rest, so therefore my initial velocity is 0. So I'm going to be using s equals to ut plus half at squared. So let's find that. 1/2 times by 3.2 times by 4 squared. So the distance travelled is 25.6 meters. And then let's have a look at this final bit. The magnitude of the normal reaction between the body and the table. So for this one, let's have a look at this black box in the bottom corner. If the object is not accelerating in a particular direction, either up, down, then the forces of up equal the forces of down. So when we try to find the magnitude of the normal reaction, normal meaning 90 degrees from where it's lying, and then reaction mean it's going upwards. So this body of mass being pulled along a table is just going left and right. It's not going up and down. So if it's not going up and down, we know that my reaction must equal the weight that's being pushed downwards, which is its mass times by gravity. So that equals to 5 times 9.8, which if I can do it in my head, 10 times would be 9.8, 98, so this is 49 newtons. I will double check that, because it's a Sunday and I don't trust my maths on a Sunday. Yep, that is true. So no actual maths done there, just understanding our forces. If something isn't accelerating in that direction, the forces are in equilibrium, balanced. Okay, that's it. I'll let you know what questions I would like you to have a go at on Show My Homework.